Tonight, when you look up, the moon will seem calm and harmless, a glowing circle that has watched over Earth since long before the first humans ever walked its surface. But there was a time when that peaceful moon almost slipped away forever. Not in a legend, not in a science fiction movie, but in the real hidden history of our planet. The young moon once hung so close it filled half the sky. Its pull tore at the oceans and twisted Earth's rotation until the entire system shook. Then the balance started to break. The moon's orbit stretched. Its path wobbled. Gravity from the sun and the planets pulled at it like invisible hands, trying to steal it away. For a moment in deep time, our moon was on the edge of escape. One small change in heat, or tide, or tilt, and the moon could have drifted out into the darkness, leaving Earth alone and unstable. And here is the part that should make you stop and pay attention. The evidence of this near disaster is still written in the rocks, in ancient tides frozen into stone, in the length of Earth's day, even in the sky above your house right now. If you are watching this in Manila on your phone, or in New York before bed, or somewhere else on the planet wide awake at midnight, get ready, because what you are about to hear will change the way you look at the moon forever. Imagine looking up at the night sky and seeing something impossible happening right in front of you. The moon is not sitting calmly in its usual place. It is drifting. Not fast enough to notice at first, but over weeks and months you would realize it is shrinking, slipping away, becoming a distant, pale dot where a glowing giant used to be. The tides that once shaped coastlines would collapse into gentle ripples. Nights would grow darker than anything humans have ever experienced. The oceans would fall silent. Our world would feel like it was slowly being unplugged from a power source we never knew we depended on. It sounds like science fiction, the kind of thing you only see in a movie where everything goes wrong in the first 10 minutes. But the truth is far stranger. There was a moment in the deep past of our planet when the moon came shockingly close to breaking free from Earth, not in the way you picture it drifting off in real time, but through a long series of cosmic events that nearly sent it on a path where escape was possible. Billions of years before humans even existed, before dinosaurs, before plants, when Earth was still young and unstable, the relationship between our planet and the moon was far more intense and dangerous than it is today. The moon sat so close to Earth that it filled the sky like a massive glowing world. Its gravity pulled on our planet with unbelievable force, creating tides that could swallow coastlines and shake the crust. Earth spun so fast that a day lasted only a few hours. The entire system was stretched tight, like a rope pulled to its limit, and deep inside that chaotic dance, there was a moment where everything we take for granted today almost vanished before it ever really formed. Most people think the moon has always been a calm companion, circling Earth in perfect balance, keeping our nights bright and our seasons steady. But the reality is that the moon has been slowly drifting away from Earth since the moment it formed. Even right now, it is moving farther from us every year. The reason is simple physics. The same tides that pull on the oceans also push on the moon. Over millions of years, those tiny pushes act like slow but powerful nudges, sending the moon outward little by little. Today the drift is gentle, but in the early days it was anything but gentle. Back then, the moon was caught in a fierce gravitational struggle between Earth and the Sunday. There were times when the pulls lined up in ways that could have stretched the moon's orbit into something unstable. If that had happened at the wrong moment, our moon might have gained enough energy to escape entirely. An Earth without a moon would not look anything like the world we know. Our seasons would swing wildly. Our tilt would wobble out of control. Life might have never risen beyond simple organisms. The moon did not just light our sky, it shaped our destiny. And the fact that it stayed with us was not guaranteed, It was the result of a fragile cosmic balance that almost failed in the first chapter of Earth's history. The story of how the moon was born does not start with peace. It does not start with calm oceans or quiet skies. It begins in a time when Earth itself was unrecognizable, a glowing world covered in boiling oceans of lava, spinning fast under a sky filled with falling rock. This was more than 4 billion years ago, long before any form of life existed, long before the planet had cooled enough for continents or oceans to even form. Earth was young, unstable, and still growing. Then something happened that changed everything. It was not a gentle event. Scientists call it the giant impact, but that name barely captures the violence of what took place. Imagine a planet-sized object, a world the size of Mars, rushing through space with unbelievable speed. This object had been circling the sun just like Earth, but small differences in their paths pulled them closer and closer until finally they collided. When the two worlds met, the energy released was beyond anything we can truly imagine. The impact was so powerful that it melted entire layers of Earth's surface and blasted enormous amounts of molten rock into space. Mountains of vaporized stone were thrown upward. The sky itself became a glowing cloud of debris. Earth shook so violently that its entire crust rippled like liquid. For a moment, it was as if the planet was being torn apart. The object that hit Earth did not survive. Much of it was destroyed on impact, mixed into Earth's molten surface, or thrown into orbit as blazing fragments. These red-hot pieces of Earth and the impacting body formed a giant ring around the planet. It was not beautiful, it was terrifying. A halo of fire and stone wrapped the young world like the rings of Saturn, except everything was made of molten rock spinning in unstable paths. Over time, that ring began to change. The debris started crashing into itself, forming larger and larger clumps. Gravity pulled the molten fragments together, shaping them into a single glowing ball. Slowly, this ball cooled and hardened. This was the beginning of the moon. But the moon did not form peacefully. It orbited extremely close to Earth, so close that it filled the sky in a way that would seem unreal to us now. The new moon tugged fiercely on the molten planet below, raising tides not in water, but in lava. Earth spun so fast that a full day lasted only a few hours. The moon raced around the planet in a wild, unstable orbit that shifted constantly as the molten Earth cooled and changed shape. Everything in the Earth-Moon system was chaotic. The sky glowed with leftover dust from the impact. Earth's crust cracked and reformed again and again. Oceans of lava rose and fell under the moon's pull. The entire world was trying to settle into a new shape after a collision that nearly destroyed it. And yet, out of this destruction, something incredible was born. A stable moon would eventually rise from the chaos. But in these early moments, nothing about its future was guaranteed. The bond between Earth and its new companion began in fire and violence, setting the stage for a relationship that almost ended before it truly began. When the moon was newly formed, it was nothing like the calm white circle we see today. It hung in the sky like a giant glowing world so close to Earth that it looked 10 times larger than it does now. If you stood on the surface of the young planet and looked up, you would have seen a massive sphere filling a huge part of the sky, bright and hot, and still cooling from the violence that created it. The newborn moon was not drifting gently around Earth. It was racing. It orbited at a distance of only a few tens of thousands of kilometers, close enough that it moved quickly across the sky every night. Earth itself spun so fast at this time that a full day lasted only a few short hours. The rapid spin and the close orbit created a gravitational struggle that shook both worlds. Because the moon was so close, Earth's gravity forced it to lock into the same face very early in its history. That means the moon became tidally locked so fast that almost no time passed before one side became the permanent far side and the other became the side that always faced Earth. From that moment on, the moon never turned its face away. It watched Earth constantly like a bright molten eye in the sky. But this closeness came with consequences. The tides the moon created were beyond anything we can imagine today. Earth at that time was still covered in oceans of lava, and those oceans rose and fell under the moon's pull in enormous waves of glowing rock. Even after the surface cooled and hardened, the tides in the early oceans were still monstrous. Water rushed across young coastlines with unbelievable force, carving the shape of the planet again and again. The moon pulled on Earth so strongly that the entire crust flexed upward and downward. The ground itself seemed to breathe under the weight of the young moon's gravity. This was not a peaceful partnership. It was a dangerous dance where both bodies were constantly pulling and pushing each other. The moon tried to move away as Earth's spin threw energy into its orbit. Earth tried to slow down as the tides dragged against its surface. Every day was a little longer than the one before. Every year, the moon moved slightly farther away. But this early stage was far from stable. The moon's orbit wobbled and stretched, sometimes pulling closer and sometimes drifting a little outward. The slightest change in speed or position could have created a path that was too stretched out to hold. In that fragile time, nothing about the moon's future was guaranteed. If its orbit had become too elongated, it might have slipped into a dangerous path where Earth could no longer hold onto it. The moon that looks so steady today began its life on the edge of chaos. It was a giant, blazing world, hovering so close that it dominated everything on Earth. Its pull shaped the tides, slowed the rotation of the planet, and carved the early landscape. The bond between Earth and the moon was powerful, but it was not secure. In those early days, the system was wild, unpredictable, and dangerously close to falling apart. Gravity works like an invisible rope, connecting Earth and the moon. You cannot see it or touch it, but it is always there, pulling on both worlds and shaping the way they move. At first, it seems strange that this invisible pull could make the moon drift farther away over time. But once you understand the tug of war happening between Earth's spin and the moon's orbit, everything starts to make sense. Imagine Earth spinning fast like a giant merry-go-round while the moon circles close by. As Earth spins, its oceans bulge outward because the moon is pulling on them. These bulges are the tides. But here is the strange part. Earth spins faster than the moon orbits, so the tidal bulge does not sit directly under the moon. It gets dragged ahead a little, almost like a wave reaching forward. That slight lead creates a twist in the invisible rope between Earth and the moon. The bulge tries to pull the moon forward in its orbit, while the moon tries to pull the bulge back into place. This tiny tug is where everything changes. When the bulge pulls on the moon, it gives the moon a little extra energy. In space, energy means motion, and motion means distance. So the moon uses that extra push to climb into a slightly higher orbit. It drifts a tiny bit farther away. This happens every day, and even though the effect is small, it never stops. Over millions of years, those small pushes pile up, and the moon slowly spirals outward. It is like giving someone gentle pushes on a swing. One push does not do much, but many pushes over a long time send the swing higher and higher. At the same time, Earth pays a price for this. When the moon takes energy from the bulge, it steals a bit of Earth's rotation. Earth spins a little slower. Days get slightly longer. A long time ago, a day on Earth lasted only a few hours. Now it lasts 24 hours, and it will continue to grow longer as the moon moves away. This exchange of energy is what scientists call the transfer of angular momentum. But you do not need big, complicated words to understand it. It is basically a trade. Earth gives up some of its spin. The moon takes that spin and turns it into orbital distance. Both bodies are locked in this trade, and they have been since the moon was born. This tug of war is not violent. It is slow and steady, like a quiet clock that never stops ticking, but it is powerful enough to reshape the entire history of Earth. It controls the tides. It changes the length of our days. And, most importantly, it is the reason the moon is drifting away even now. Without this invisible rope and the energy it moves between the two worlds, the moon might have fallen into a dangerous orbit or even crashed back into Earth. Instead, it glides outward in a slow, graceful spiral that has lasted billions of years. When you think about gravity, you usually imagine one object pulling on another, but in space things get much more complicated than that. Objects do not just pull, they tug in patterns, again and again. And sometimes those repeating tugs line up in a way that changes everything. This is what scientists call resonance, and it can turn gentle gravitational nudges into forces strong enough to reshape entire orbits. To understand it, imagine someone pushing a swing. If they push at random times, nothing special happens. The swing just moves a little and slows down again. But if they push at the exact right moment each time the swing goes higher and higher, the timing matters more than the strength of the push. In space, the same thing happens, except the swings are moons and planets and the pushes are tiny gravitational pulls. When their timing matches, even a small repeated tug can build up into something powerful. Long ago, when the moon was still young and far closer to Earth, the two worlds danced through a time where these repeated tugs may have lined up almost perfectly. Earth was spinning quickly. The moon was spiraling outward. The sun was pulling on both of them from far away. All three of these motions created a pattern, and sometimes those patterns matched in a way that could amplify the moon's movement instead of slowing it. This is what scientists call an orbital resonance. It is like the universe hitting the exact right rhythm to push the moon harder and harder. During this early era, the Earth-Moon system may have drifted into the first great resonance, a moment when the timing of Earth's spin, the moon's orbit, and the pull of the sun lined up exactly wrong. Normally, Earth's tides act like a brake on the system. They slow Earth's spin and gently push the moon outward in a controlled way. But in a resonance, the pushes from the sun can add energy to the moon's orbit instead of taking it away. It is like someone else suddenly joins in on the swing, pushing at the perfect moment every time. The moon starts gaining energy faster than usual, and its orbit begins to stretch. A stretched orbit is dangerous. It brings the moon closer at one end and much farther at the other. If it stretches too much, the gravity holding the moon in place can weaken for a brief moment. And in the early unstable days of the solar system, even a brief moment could have been enough to send the moon onto a path that did not circle Earth anymore. Scientists studying ancient orbital patterns have found clues that the Earth-Moon system came near one of these resonant configurations billions of years ago. It is impossible to know exactly how close it got, but the models show something surprising. The system did not have much room for error. A slightly different angle of impact when the moon formed a slightly different rotation rate for Earth, or a slightly stronger pull from the sun could have lined up the resonance perfectly. If that had happened, the moon might have been pushed into an orbit that was too stretched, too unstable, and too energetic for Earth to hold. Instead, we survived the first great resonance, and the moon stayed. But this moment in deep time shows just how fragile the early Earth-Moon relationship really was. The bond that seems so steady today once hung on the timing of invisible tugs in a cosmic rhythm that almost broke the system apart. When scientists first began studying the early history of the moon, they expected to find a simple story. The moon formed. It moved outward. Earth slowed down. That was it. But the more they studied the motions of planets and moons, the more they realized that the past was anything but simple. Hidden inside the ancient Earth-Moon system was a dangerous trap, a kind of cosmic rhythm that could have sent the Moon into a wild orbit. This trap is known as the evection resonance, and it is one of the most important discoveries in understanding how close the Moon came to escaping Earth altogether. The story of this discovery begins with scientists running simulations of the early solar system. They wanted to understand how the Moon's orbit might have changed over billions of years. When they put in all the known variables, the young, fast, spinning Earth, the close hot Moon, and the steady pull of the Sun, something strange appeared in the data. The Moon's orbit began to stretch more than expected. It was not just moving outward, it was becoming more elongated, like someone pulling on a rubber band. At first, the scientists thought there was a mistake in the models, but the stretching kept happening no matter how many times they ran the simulations. The only explanation was that the Moon had been caught in a special kind of resonance, one that acted very differently from normal gravitational tugs. This resonance appeared when the motion of the Moon lined up exactly with the motion of Earth around the Sunday. It meant that every time the Moon reached a certain point in its orbit, the Sun pulled on it in the same direction and with the same timing. The Sun was giving the Moon regular pushes at the perfect moments. These pushes did not make the Moon go faster in a circle. They stretched the orbit. They pumped up its eccentricity, which is the scientific word for how stretched an orbit is. The more eccentric the orbit became, the more uneven the Moon's distance from Earth grew. Sometimes it came dangerously close, and other times it swung far away. This was the evection resonance, a moment in deep time when the Sun's repeated tugs lined up with the Moon's motion in a way that could have turned the orbit unstable. The more scientists studied it, the more they realized how serious this was. If the eccentricity had grown too much, the Moon might have reached a point where Earth's gravity could no longer pull it back in. It could have been boosted into an escape path. No Earth-Moon system, no steady tides, no stable seasons, no calm nights. The entire history of our planet would have changed. What makes the evection trap even more shocking is how easy it would have been for the Moon to fall into it permanently. A slightly different rotation speed for early Earth, or a slightly different distance for the young Moon, could have locked the system into the resonance long enough to send the Moon drifting toward freedom. The fact that it did not happen feels almost unbelievable. The Earth-Moon system slipped into the resonance but slipped out again before the orbit became too stretched. Scientists still do not fully understand every detail about how the escape happened, but one thing is clear. The early Earth-Moon system walked right up to the edge of disaster. The evection resonance was a cosmic trap that almost changed the future of our world, and the Moon barely made it through. When the Moon's orbit begins to stretch, it changes everything about the way it moves around Earth. Instead of following a smooth circle, it starts following an oval path that brings it much closer at one end and much farther at the other. Scientists call the closest point perigee and the farthest point apogee. In the early Earth-Moon system, this stretching was not gentle. It was dramatic enough to create moments where the Moon loomed huge in the sky and then later shrank into a distant pale shape. A Moon on a stretched orbit is a Moon on a leash that keeps pulling tighter and looser with every cycle. At perigee, the Moon would have been close enough to turn tides into towering walls of water. These tides were nothing like the calm rising and falling we know today. They could have rushed inland with enormous force, tearing apart coastlines and reshaping the young planet again and again. The ground itself would have flexed under the strain. Entire regions could have lifted and dropped as the Moon made its close approach. The energy released during these tidal surges would have heated the crust and changed the flow of early oceans. Life did not exist yet, but if it had, this world would have been almost impossible to survive. Then, at apogee, everything reversed. The Moon drifted far away, The tides weakened. Nights grew darker. The pull that had been ripping at the planet became a distant whisper. Earth went from violent shaking to eerie calm in a single orbit. This constant switching made the entire Earth-Moon system unstable. It is like spinning a weight on the end of a rope that keeps changing length. The motion becomes unpredictable and dangerous. And every time the Moon reached perigee, it gained or lost tiny amounts of energy depending on the angle of its orbit. A stretched orbit can give the Moon a boost in the same way pushing a swing at the right moment sends it higher. If this boost happens again and again, the Moon collects energy. The more energy it has, the harder it is for Earth's gravity to keep it in orbit. Scientists studying the early system realized that if the Moon's orbit kept stretching more and more, it could eventually reach a point where its apogee grew too large. At that point, the Moon would drift so far that Earth's gravity would not be strong enough to pull it back into a safe loop. The Moon would not simply float away. It would break from the orbit in a slow, long motion that could end with it traveling into deep space or falling under the influence of the Sun instead. An Earth without the Moon would be a completely different world. Its rotation could wobble wildly. Its seasons could twist out of balance. Tides would shrink so much that the rhythm of the oceans would be lost. Everything from climate to the development of life would change. The early Earth came very close to this scenario. The stretched leash of the Moon's orbit pulled the system toward a tipping point. Tiny changes in distance and motion could have sent the Moon on a path that no longer circled Earth. Instead, the Moon remained bound, but barely. The stretching stopped before it reached the point of no return. The Earth-Moon connection survived, but it was a fragile victory won in a time when the whole system could have unraveled. When people think about orbits, they usually imagine perfect circles that never change. But the truth is that an orbit is nothing more than a balance of speed and gravity. If something goes a little faster than before, its orbit grows wider. If it goes too fast, gravity cannot hold it anymore. It breaks free. This is called escape, and it can happen to moons, planets, comets, or anything else moving through space. All you need is enough energy in the right direction. Imagine swinging a ball on a rope. As long as the rope stays tight, the ball keeps moving around you. But if the ball speeds up too much, or the rope becomes loose at the wrong moment, the ball flies off in a straight line, it will not circle you anymore. That is exactly what happens when orbits go rogue. A moon moving around a planet is held in place by gravity, but it is also always moving forward. If the forward motion becomes too strong, gravity loses the fight. The Moon leaves the orbit, and the system is broken. For the Moon, this would not look dramatic in real time. It would not suddenly zoom away. Instead, the highest point of its orbit would grow a little more each cycle. The distance at apogee would stretch. Earth's gravity would reach out and try to pull the Moon back, but each time the pull would weaken. If the Moon collected enough extra energy, its orbit could eventually become so wide that it slipped past the limit where Earth could no longer hold it. At that point, the Moon would no longer be a moon. It would become an object drifting freely through the solar system. Scientists know this because escape is a normal part of orbital physics. It has happened to moons around other planets. It happens to comets pushed by the gravity of giant worlds. It even happens to spacecraft when they fire their engines to leave a planet behind. The early Earth-Moon system had everything needed to make this possible. The Moon was still young and hot. Earth was spinning much faster than it does today. The tides were massive, and the Sun's pull was constantly interfering with the orbit. Every one of these forces added or removed energy from the system. The Moon gained energy from Earth's rotation as the tides dragged forward. It gained even more when the Sun pulled at the right moments. And when the orbit stretched during the evection trap, the Moon reached distances where the balance between forward motion and gravitational pull grew dangerously thin. Models of the early system show that the moon's orbit came close to the range where escape becomes possible. Even small differences in timing or distance could have sent the moon on a path that drifted wider and wider until Earth could not pull it back. A slightly stronger push at the wrong moment, or a slightly longer time spent in a stretched orbit, could have set the moon free. The fact that the moon stayed with Earth was not guaranteed. It was the result of a chaotic early system that somehow settled into balance instead of breaking apart. The moon remained a satellite, but it came close to becoming a wanderer, lost in the vast, empty space between worlds. If you want to understand what happened to the moon billions of years ago, you cannot go back in time and see it with your own eyes. There are no cameras waiting in ancient space, and no written records from the age when Earth was still cooling. But there are clues, and they are hidden in the most unexpected places. Tidal mud, ancient rock layers, patterns frozen into stone that formed long before humans existed. Scientists who study these clues are like detectives working on a case older than life itself. They are dynamicists, geophysicists, and planetary scientists, and their job is to read the history of the Earth-Moon system the same way a paleontologist reads the bones of dinosaurs. Instead of bones, they study rhythms locked inside the rocks. One of their most powerful tools is something called a tidal rhythmite. These are layers of sediment that formed in ancient tidal zones hundreds of millions of years ago. Every tide left a thin deposit of mud, then the next tide added another and another, until the layers stacked up like pages in a book. If you look closely, these layers reveal patterns. Some layers are thick, some are thin, some form repeating groups. These patterns tell scientists how strong the tides were at the time and how often they rose and fell. Since the tides depend on the moon's distance and Earth's rotation, the rocks become a record of the ancient orbit. It is like finding a fossil of time itself. Scientists have found tidal rhythmites in places like Australia and Canada that formed hundreds of millions of years before humans appeared. When they counted the layers, they discovered something incredible. Earth used to have more days in a year because the days were shorter. The moon used to be much closer. These numbers match the predictions made by orbital models, showing that the moon has been drifting outward for billions of years. Another group of scientists uses computer models to recreate the early Earth-Moon system. These models take everything into account: Earth's spin, the pull of the sun, the shape of the oceans, the way tides move energy, and even the heat inside the planet. The computers run these simulations forward and backward over enormous stretches of time until they match what the rocks show. When the numbers line up, the scientists know they are close to the truth. Other clues come from the moon itself. The Apollo missions in the late 1960s and early 1970s brought back rocks from the lunar surface. These rocks are ancient, nearly as old as the solar system. Their chemistry reveals how quickly the moon cooled and how its orbit changed as it moved outward. The rocks even show signs of how strong Earth's tides once were, because tidal heating on the moon left scars inside its crust. By putting all of these clues together, the scientists can reconstruct the path the moon took through deep time. They can see moments where the orbit stretched, moments where Earth's spin slowed faster than expected, and moments where the system came close to dangerous resonances. They are piecing together a story that spans billions of years, using nothing but stone, light, equations, and patience. The paleontologists of orbits are uncovering the truth of how the moon almost broke free and how close the Earth-Moon system came to losing the companion that shapes every night. Their work shows that the story of the moon is not just written in the sky, it is written in the ground beneath our feet. When you hear the word fossil, you probably think of bones trapped in stone. But some of the most important fossils in Earth's history are not bones at all. They are patterns in ancient mud left behind by tides that rose and fell hundreds of millions of years ago. These patterns are called tidal rhythmites, and they act like time capsules. They carry information about how long a day was, how fast Earth was spinning, and how close the moon used to be. All of this is written in thin layers of sediment that look simple on the surface, but hide an incredible story inside. To understand how it works, imagine standing on a beach where the tide comes in and goes out twice a day. Every time the water rises, it brings sediment with it. When the water pulls back, it leaves some of that sediment behind. Over time, the layers build up tiny sheets stacked one on top of another. In most places, waves or storms erase these patterns. But in a few rare locations, everything stayed perfectly still, long enough for the layers to freeze in place. These places became natural recorders, keeping track of each tide like the ticks of a clock. Millions of tides later, the layers hardened into rock, and today, scientists can read them the same way someone reads lines in a diary. Some of the best tidal rhythmites ever found come from places like the Elatina Formation in Australia. These rocks formed more than 600 million years ago. When scientists sliced them open, they saw repeating bands of thick and thin layers. Each thick layer represented a stronger tide. Each thin layer represented a weaker one. By counting how many layers formed between each strong tide, they discovered something amazing. There were more daily layers in every cycle than we have now. That meant a day back then was shorter. The only way that could happen is if Earth was spinning faster. And if Earth was spinning faster, the moon must have been closer because the moon's pull is what slows Earth down. The rocks had become a fossil of time, measuring the spin of Earth like a clock. Some rhythmites even showed that an ancient year held more than 400 days. Not because the year was longer, but because the days were shorter. Earth had been rotating so quickly that one full spin took only about 20 hours. Tides were stronger back then because the moon was closer. Scientists could calculate exactly how close by using the patterns in the rocks and comparing them to modern tidal cycles. When they did the math, the numbers matched the idea that the moon has been steadily drifting away at a slow but constant rate. The distance today is about 380,000 kilometers, but hundreds of millions of years ago, it was tens of thousands of kilometers closer. This outward drift is caused by the same tidal forces that left their fingerprints in the rhythmites. That means these ancient patterns are not just pretty geological features. They are physical proof that the moon is moving away and has been since the beginning. Each layer carries the memory of a world that spun faster, a moon that loomed larger in the sky, and tides that shook the young Earth. These fossils of time show that the Earth-Moon system has always been changing, and without these delicate layers preserved for hundreds of millions of years, we might never have known how far the moon has travelled. There was a time in Earth's past when a day did not last 24 hours. It did not even last 20. Instead, the entire planet spun so fast that sunrise and sunset passed in only 18 hours. If you could have stood on Earth during that era, the world would have felt restless, rushing through daylight and darkness like it was in a hurry to get somewhere. This was not a small difference. An 18-hour day meant Earth was rotating almost a third faster than it does now. And whenever Earth spun faster, the moon sat closer in the sky, pulled inward by the same tides that tried to slow the planet down. The sky then would have looked almost unreal. The moon appeared much larger, hanging over the horizon like a glowing giant. Its gravity pulled on the oceans with incredible strength, creating massive tides that rolled across early coastlines. The Earth-Moon system was far more intense back then, like a machine running at full speed with gears grinding against each other. Scientists discovered this snapshot of time by studying tidal rhythmites and ancient coral growth lines, which preserve information about how long days and years used to be. These rocks and fossils show that hundreds of millions of years ago, Earth spun faster, and the moon orbited closer because the tidal pull between the two was stronger. But there is also something else hidden in this 18-hour world. The faster Earth spun, the more energy it poured into the moon's orbit. Every tide that bulged forward gave the moon a little nudge outward. But while the moon drifted away, it also slipped in and out of gravitational patterns with the Sunday. These patterns are the resonances that could push the moon's orbit into dangerous shapes. When the moon was closer, these resonances were easier to hit. The system did not have to drift far before everything aligned in just the right way to amplify the moon's motion. In the 18-hour era, the Earth-Moon system moved through these risky zones more often. The whole orbit felt like a tightrope walk. A slight change in Earth's rotation, a tiny shift in the shape of the tides, or a small alteration in the pull from the sun could have stretched the moon's path. A stretched orbit meant the moon would come closer at one point, then swing farther out at another. If the stretching grew strong enough, the moon could collect too much energy. Scientists running simulations of this period found that the system was much more chaotic and sensitive to small changes. The moon's orbit was not a calm circle. It wobbled, it tilted, it pulsed outward and inward as Earth slowed down and the sun pulled from the side. The entire system was racing through deep time with a level of instability we cannot see today. An 18-hour day was more than just a faster spin. It was a sign of how young and wild Earth still was. The tides were powerful. The moon was bold in the sky. And the Earth-Moon system was drifting in and out of dangerous resonances that could have changed the story of our world. This snapshot reveals a moment when everything was moving quickly and nothing was guaranteed. It was a time when the moon's fate hung on the delicate balance between speed, gravity, and timing. And somehow, that balance held long enough for the system to survive. When you look at the moon in the night sky, it feels like a simple system. Earth pulls on the moon pulls on Earth. Everything moves in smooth, predictable cycles. But when you zoom out and look at the entire solar system, you see that nothing about these orbits is simple. Earth and the moon are not dancing alone. They are surrounded by giant planets, inner worlds, and the endless pull of the Sunday. Each one of these bodies tugs on the Earth-Moon system in tiny ways, and those tiny tugs can build into something much larger. The early solar system was like a massive pinball machine, where even the smallest bump could send a planet or moon onto a new path. Start with the Sun, the largest mass in the whole system. Its gravity controls everything. It pulls on Earth and the moon with overwhelming force. It shapes the length of our year, the shape of our orbit, and the timing of our seasons. But the sun also pulls directly on the moon. When the moon reaches certain points in its orbit, the sun gives it little nudges. Most of the time, those nudges do nothing serious. They simply add or subtract a tiny bit of energy. But when they line up with the moon's natural motion, they can amplify its orbit, stretching it or twisting it into different shapes. Now add Jupiter to the picture. Jupiter is more than 300 times the mass of Earth. Even from hundreds of millions of kilometers away, its gravity still reaches us. Jupiter's pull affects Earth's orbit, Earth's tilt, and the long-term stability of the solar system. Scientists running detailed simulations have discovered that Jupiter creates slow, gentle waves in Earth's path around the Sunday. These waves change how far Earth tilts and how our seasons behave over tens of thousands of years. When the moon was closer, these waves would have been even more powerful because the Earth-Moon system was more sensitive to outside forces. A slight shift in Earth's orbit caused by Jupiter could change the timing of the tides or the distance of the moon by just enough to push the system toward a resonance. Venus also plays a role, even though it is much smaller than Jupiter. Because Venus orbits close to Earth, the gravitational connection between the two planets is strong enough to change Earth's rotation speed and orbital shape over long stretches of time. Imagine Earth and Venus passing each other again and again like two heavy magnets. Each pass gives a tiny pull, and over millions of years those pulls add up. If the Earth-Moon system was already unstable, even a small tug from Venus could shift the Moon's orbit into a new pattern. When you combine all of these forces, you get a picture of a young Earth-Moon system living in constant motion. The Sun pulling from the center, Jupiter tugging from afar like a giant unseen hand, Venus brushing past on the inside lane, all of them influencing Earth's path, and therefore influencing the Moon's path too. It was a delicate balance, a shift of a few percent in Earth's orbit, a slight change in the angle of the Moon's path, a tiny variation in how tides moved energy. All of these could have sent the Moon drifting into or out of dangerous resonances. In those early ages, the Earth-Moon system was not a peaceful pair orbiting alone in space. It was a small part of a giant cosmic pinball machine, where every planet had a chance to bump the system into a new direction. The fact that Earth kept the Moon at all is proof of how lucky and balanced the system eventually became. Without that balance, the Moon could have been knocked into a path that led away from Earth forever. When scientists tried to understand what happened to the Moon billions of years ago, they turned to powerful computer simulations. These programs take in everything we know about gravity, tides, rotation, and the pull of the Sun and the planets. Then they run the clock backward to the age when Earth was young and the Moon was glowing hot and dangerously close. What the simulations show is not a calm, predictable orbit. They show a system that could have tipped into disaster with the smallest change. One of the most surprising discoveries is how easily the Moon's orbit could have become extremely eccentric. Eccentric means stretched out. Instead of moving in a near circle, the Moon would follow a long oval path that swung it close to Earth at one end and far away at the other. In some simulation runs, the orbit becomes so stretched that the Moon passes close enough to create massive tides, and then swings far enough away that Earth's gravity struggles to pull it back. These are the moments when the Moon flirts with instability. In every simulation, the dangerous part begins the same way. The Moon spirals outward as Earth slows down. The Sun pulls from the side in regular patterns. Then at just the wrong moment, the rhythm lines up. The Sun begins giving the Moon tiny, steady pushes at exactly the right time each orbit. These pushes stretch the path a little more with every cycle. The eccentricity grows. Earth tries to pull the Moon back into a safer shape, but the forces are too balanced. Once the orbit begins to stretch, the system becomes extremely sensitive. In the simulations, a difference as small as a fraction of a degree in the Moon's tilt, or a change of a few kilometers in its distance, can completely alter the outcome. In one version, the orbit stretches so much that the Moon reaches a point where Earth's gravity is barely strong enough to hold it. The Moon begins drifting farther at apogee until it is almost out of the planet's control. If the simulation continues, the Moon eventually escapes and becomes a wandering object circling the Sunday Earth, is left with no large Moon, and a future far different from the one we know. But change one detail and everything shifts. If Earth slows down a little faster, or the tides move energy slightly differently, or the Sun's tug arrives just a little out of rhythm, the resonance collapses. The stretching stops. The orbit stabilizes. The Moon stays bound. It is shocking how small the difference needs to be. Two simulations that start from nearly identical conditions can end with two completely different versions of history. In one, Earth loses its Moon. In the other, Earth keeps it. This tells scientists something important. The early Earth-Moon system was balanced on a razor edge. The path between survival and escape was incredibly narrow. Yet somehow, the real universe chose the version where the Moon stayed. The simulations reveal that our moon is not here because the system was perfectly stable. It is here because a series of tiny lucky differences kept its orbit from becoming too eccentric. It was a narrow escape written into the earliest chapters of our world. In the earliest days of Earth's history, the surface of the planet was nothing like the cool, solid world we live on now. Instead, Earth was covered in a deep ocean of magma, a glowing sea of molten rock stretching across the entire planet. Temperatures were so high that even the crust could not harden for long. Everything churned, flowed, and boiled. This strange landscape played a huge role in the fate of the moon. When Earth was still soft and molten, it reacted to the moon's gravity in a way that no solid planet ever could. The moon pulled on the magma ocean, just like it pulls on our modern seas. But the response was far more dramatic. Instead of gentle tides rising and falling by a few meters, the molten surface heaved upward in enormous, slow-moving waves of liquid rock. These tides were powerful enough to reshape the entire planet's surface again and again. They created mountains of molten material that rose and then collapsed back into the glowing ocean. All of this motion mattered because tides do more than just move material. They drain energy from the system. Every time the magma shifted, Earth lost a bit of its rotation. That lost rotational energy did not disappear. Some of it turned into heat inside the magma ocean, and the rest was transferred to the moon's orbit. Normally, that exchange would push the moon outward, making it drift away faster. But when Earth was still molten, something else happened. The tides in the magma ocean were so huge that they absorbed enormous amounts of energy. They acted like a giant planetary brake, slowing the whole Earth-Moon system down. Instead of giving the moon too much energy and letting it escape, the magma tides soaked up much of the energy that would have stretched the moon's orbit dangerously. The soft molten Earth flexed and shifted easily, and this flexibility helped keep the orbit from growing too eccentric. In the computer simulations scientists ran, when Earth is modelled as a solid planet, the moon often ends up drifting into unstable orbits, especially during resonances. But when Earth is modelled as a semi-molten world, the tides become far more effective at bleeding off orbital energy. The moon's orbit stays rounder. The dangerous resonances weaken. The risk of escape drops dramatically. It turns out that the very thing that made early Earth so chaotic, its molten surface and magma ocean, may have been the reason the moon remained bound to it. The magma ocean did not just glow under the young moon's pull. It shielded Earth from losing its companion. As Earth cooled and hardened over millions of years, the tides changed. They became smaller and weaker because solid rock does not flex the way molten rock does. But by then the worst dangers had passed. The moon had moved far enough away that the most dangerous resonances were no longer in reach. The early molten Earth acted as a stabilizer during the most vulnerable period of the Earth-Moon relationship. It slowed Earth's spin, soaked up energy, and prevented the moon from drifting into a stretched orbit that might have sent it on a path to freedom. The magma ocean was not just a stage in Earth's fiery birth. It was a protective shield that kept the moon close long enough for the system to survive. When Earth finally cooled enough for a solid crust to form, the planet entered a new chapter in its history. The endless magma oceans hardened, volcanoes built the first islands, and over millions of years, those islands merged into the earliest continents. At the same time, Earth's atmosphere thickened, temperatures dropped, and water collected into the first deep oceans. These changes did more than reshape the surface of the world. They transformed the way tides moved, and those tidal changes played a hidden but powerful role in keeping the moon safely bound to Earth. In the beginning, Earth's molten surface had flexed easily under the moon's pull. But once continents appeared, everything became more complicated. Continents acted like giant barriers rising out of the sea. They blocked, redirected, and trapped the motion of the tides. Water could no longer flow smoothly across the entire planet. Instead, it had to slosh through narrow passages around coastlines and against underwater mountains. This made the tides stronger in some places and weaker in others. The shape of the oceans themselves mattered too. Deep oceans react to tidal forces very differently from shallow seas. In deep water, the tide can move freely, creating slow, powerful waves that push enormous amounts of energy around the planet. In shallow water, the tide becomes faster and more chaotic, building up steep waves that crash against the coast with far more force. As Earth formed its first deep oceans, the tides began to change from smooth rhythmic pulses into complex patterns that varied from one region to another. These new patterns changed how much energy the tides could take from Earth's rotation. The braking effect of the tides grew stronger and more variable. Sometimes the tides slowed Earth quickly. Other times, they slowed it more gently. All of this mattered because the amount of braking changed how the Moon's orbit evolved. When Earth slowed faster, the Moon gained more outward push. When Earth slowed more gradually, the Moon drifted outward more gently. Over long stretches of time, these changes helped smooth the Moon's orbit, keeping it closer to a circular shape instead of letting it stretch into the dangerous ovals that almost tore the system apart. The continents also helped by breaking the symmetry of the tides. A planet covered only in ocean would let tides move in clean, simple waves that might line up too easily with solar forces, increasing the risk of resonances. But a planet with continents forces tides to break apart into smaller waves with different rhythms. These rhythms are harder to match with the sun's gravitational timing. That means fewer chances for the system to slip into resonances like the evection trap. The oceans played their own part. As they grew deeper, they gained the ability to absorb more energy from the tides. This acted like a secondary brake. When the Moon tried to stretch its orbit into an elongated path, the energy got absorbed by the oceans instead of feeding the orbit. Over millions of years, this effect helped circularize the Moon's path, smoothing out the wobbling and the stretching. It locked the Moon into a safer and more stable orbit. By the time Earth's continents and oceans started to resemble the world, we know the most dangerous period of the Earth-Moon relationship had already passed. The continents anchored the tides. The oceans absorbed energy. Together, they turned the chaotic early system into something calmer and more predictable. Without continents and deep oceans, the Moon's orbit might have stayed unstable much longer. It might have slipped into a stretching loop again. It might have wandered toward freedom. Instead, Earth's changing surface helped hold the Moon close, guiding the system toward the stable partnership that has lasted for billions of years. Earth does not spin straight up and down. It tilts. Right now, that tilt is a little over 23 degrees, and that simple angle is what gives us seasons. When the northern hemisphere leans toward the sun, it gets summer. When it leans away, it gets winter. The same happens in the southern hemisphere, but in reverse. This tilt is one of the most important parts of Earth's climate, but it is also incredibly fragile. It does not stay perfectly steady on its own. It wobbles slowly, like a spinning top. If left alone, the wobble could grow wild, swinging Earth's tilt from almost no angle at all to angles so huge that the poles could point directly at the Sunday. That kind of chaos would turn Earth into a world of extreme climate changes, where ice ages and heat waves arrived without pattern or warning. But that never happened. The reason is the Moon. The Moon acts like a stabilizer on Earth's spin. Its gravity pulls on the slight bulge around Earth's middle, the bulge caused by Earth's rotation. This pull prevents the tilt from wandering too far in any direction. It keeps the wobble gentle and predictable. Without the moon, the tilt could jump dozens of degrees over a few million years. That may sound slow to us, but for a planet's climate, it is violent. The moon's steady pull keeps Earth's seasons calm and regular. Scientists studying planets around other stars have found that many Earth-sized worlds do not have large moons. Without a moon to stabilize them, these planets can tilt so wildly that their climates flip between freezing worlds locked in ice and scorching worlds nearly unlivable. Earth avoided that fate because the moon has been holding our axis steady for billions of years. But the story does not end there. The tilt does more than shape seasons. It feeds back into tides. When the tilt changes even slightly, the way sunlight hits Earth changes. Ice grows or melts, oceans rise or fall, weather patterns shift. These changes can alter how tides move energy around the planet. A world with more ice pushes ocean water into different basins. A world with less ice changes the depth and temperature of the seas. Every change in the tides affects the moon's orbit because the tides act as a brake on Earth's spin and a push on the moon's motion. So the tilt and the tides are linked. If Earth's tilt had ever swung too far, it would have changed the tides enough to alter the moon's path. Maybe the moon would have slipped into one of those dangerous resonances. Maybe its orbit would have stretched again. Maybe the system would have become unstable. Instead, the moon kept Earth's tilt steady. The steady tilt kept the tides predictable. The predictable tides kept the moon in a safer orbit. It is a feedback loop that has protected the Earth-Moon system since the beginning. When you look at the moon, you are not just seeing a glowing rock. You are seeing the stabilizer of Earth's seasons, the anchor of our climate, and one of the reasons the planet did not spiral into chaos. The tilt of our world and the orbit of our moon are linked in a delicate partnership that has lasted billions of years. Without that partnership, Earth would be a tilted world spinning through a climate we might not survive. Earth's climate has never been calm. It swings between warm periods and icy ages, rising seas and falling coastlines, forests spreading and deserts taking over. At first, these changes seem disconnected from the moon, but they are part of the same long chain of feedback loops that kept the Earth-Moon system stable instead of letting the moon drift into a path that could have torn it away. Climate changes the tides, and tides change the moon's orbit. The moon then changes Earth's rotation and tilt, which affects the climate all over again. It is a loop that has been running for billions of years. During ice ages, massive sheets of ice build up across the continents. These sheets weigh down the land, pushing parts of Earth's crust lower and changing the shape of ocean basins. When ocean basins change, the tides change. Water sloshes through new paths, hits new coastlines, and reacts differently to the pull of the moon. Sometimes this strengthens the tides, sometimes it weakens them. When the tides strengthen, they pull harder on Earth, slowing its rotation a little faster and giving the moon a stronger push outward. When the tides weaken, Earth slows down more gently and the moon moves outward more slowly. Both of these changes matter because the speed of the moon's recession affects whether it drifts into dangerous resonances. If the moon moves outward too quickly at the wrong moment, it could hit one of those resonant zones that stretch its orbit. If it moves too slowly, the system could fall into a different, unstable configuration. Somehow, Earth's climate changes acted like a natural balancing system. As ice ages came and went, the tides shifted rhythmically. These shifts nudged the moon's orbit towards safer paths, smoothing out the places where the orbit could have become too eccentric. Sea level changes also played a role. When ice melts during warm periods, sea levels rise, flooding coastlines and creating new ocean shapes. When ice grows during cold periods, sea levels fall, exposing land and changing the way water moves. Each new coastline acts like a new boundary for the tides. These boundaries change how tidal energy is absorbed and where it is released. This affects how much of Earth's rotational energy gets turned into heat instead of being passed to the Moon. In some periods, this meant less energy reached the Moon, preventing dangerous boosts to its orbit. In others, it meant more braking on Earth, keeping the recession at a steady pace. Even small changes mattered. A shift in sea level by just a few hundred meters could reshape entire tidal systems. Those changes could alter how energy moved between Earth and the Moon. Over millions of years, these tiny adjustments helped guide the Moon's orbit through a maze of potential hazards. Earth's atmosphere also joined the feedback loop. Climate affects wind patterns, storm systems, and ocean currents. These forces push water across the oceans in ways that strengthen or weaken the tides. Stronger winds and higher waves during certain warm periods may have helped increase tidal friction, draining more energy from Earth's spin. In cold periods, calmer oceans may have reduced that friction. All of this influenced how the Moon drifted outward. It is almost as if Earth's climate and the Moon's orbit were having a long, slow conversation across deep time. One changed, then the other responded. That response changed the next shift, which altered the next tide, which adjusted the next step of the orbit. Without these feedback loops, the Moon might not be where it is today. It could have slipped into a stretched orbit during a warm period, or been pushed into a dangerous resonance during a colder one. Instead, the climate changes created a natural balancing act that kept the Moon safely bound. The Earth-Moon system survived because both worlds evolved together, connected by tides, shaped by climate, and stabilized by a gravitational partnership that protected the system from chaos. In another version of history, one so close to ours that the difference could fit in the space of a single moment, the Moon never became the quiet companion we know. Instead, it wandered. All it would have taken was a slightly different angle during the giant impact that created it, a little more spin in the early Earth, a magma ocean that cooled a bit too quickly. Any of these tiny changes could have pushed the Earth-Moon system onto a different path, one where the Moon slowly drifted outward until it no longer circled Earth at all. Imagine the giant impact happening just a few degrees off from the real angle. The debris cloud still forms. The molten fragments still clump together to become the Moon. But the young Moon ends up orbiting just a little farther away than it did in our timeline. That small extra distance means the tides it raises on Earth are slightly weaker. Weaker tides mean less braking on Earth's spin. Less braking means Earth rotates faster for longer. A fast rotating Earth pours more energy into the Moon's orbit. In this alternate world, the Moon spirals outward at a faster pace. At first, nothing seems dangerous. The Moon climbs into a higher orbit, just as it did in our history. But then, at the wrong moment, this faster outward motion carries it straight into the evection resonance. The timing is perfect in the worst possible way. The Sun's pull begins stretching the orbit, pumping energy into it over and over again. The Moon begins swinging closer at one end and much farther at the other. Each cycle stretches it more. Earth's gravity still tries to pull it back, but in this timeline the tides are not strong enough to counter the resonance. The orbit keeps growing more eccentric. Each apogee reaches farther into space. Eventually, one apogee crosses the invisible limit, where Earth's pull can no longer keep the Moon bound. The Moon drifts outward just a little too far. That tiny extra drift is enough to break the orbit. The Moon does not fly away suddenly, it simply fails to return. It slides gently into a new path that orbits the Sun instead of Earth. Within a few thousand years, it becomes a wandering minor planet tracing a lonely path through the solar system. Earth is left forever without a Moon. But there are other alternate worlds too. In one version, Earth's early interior is stiffer. The mantle cools more quickly. A cooler mantle means weaker tidal dissipation. which means Earth loses less rotational energy to the tides. Again, the moon moves outward faster. Again, the timing lines up with a dangerous resonance. Again, the orbit stretches until it breaks. In yet another version, Earth forms continents earlier or in different shapes. These new coastlines change how the tides move. Instead of absorbing enough energy to keep the moon's orbit round, they accidentally reinforce the dangerous stretching cycles. The moon enters an unstable shape and never fully recovers. By the time the resonance ends, the orbit is already too elongated, and Earth's gravity can no longer keep the moon close. Even the moon's internal structure matters. If its core were a little larger, or its crust a little thicker, the way it absorbed tidal energy would change. A moon that absorbs too little energy ends up with too much momentum. That momentum helps push it outward faster, once again risking escape. All of these alternate timelines share one thing. The moon only needed a small difference, one tiny change in its early conditions, to slip into a path that led away from Earth. In our world, those tiny changes never happened. The moon stayed just close enough. The tides stayed just strong enough. The cooling stayed just slow enough. The Earth-Moon system walked a narrow tightrope through its early history, and somehow our timeline is the one where the moon remained. But it is sobering to realize how easily things could have gone the other way. In a universe shaped by chaos and coincidence, there are countless worlds where the skies are dark, the tides are weak, and the moon is nothing more than a wandering ghost drifting through space. Imagine looking up at the night sky and seeing nothing but stars, no glowing circle, no familiar phases, no bright guide for travelers or anchor for the tides, just darkness. That is what Earth would look like if the moon had slipped away in the early days of the solar system. But the missing moon would be more than an empty sky. It would reshape the entire planet in ways that touch every part of life. Start with Earth's tilt. Without the moon to stabilize it, the tilt would wander wildly. Some eras might have a tilt of only a few degrees. In those times, seasons would barely exist. Winters and summers would feel almost the same, but then over thousands of years the tilt could swing the other way, reaching angles so extreme that the poles pointed almost directly at the Sunday. In those periods, one hemisphere could bake in endless sunlight, while the other froze in permanent night. Climate would swing between calm and catastrophic. Ice ages could arrive and vanish in strange patterns. Deserts might appear overnight on continents that once held lush forests. Storm systems would shift unpredictably, and ocean currents would twist into new routes without warning. Life would struggle to adapt to a world where the rules changed constantly. Next come the tides. Without the moon, the tides would be far weaker. Only the sun would pull on the oceans, and the solar tide is less than half the strength of the lunar tide. Coastlines would barely shift each day. The gentle rise and fall that shaped Earth's early coastal ecosystems would vanish. The tidal pools that may have helped early life move from sea to land might never form. Even today, many species depend on the rhythm of the tides to feed, migrate, or reproduce. Without that rhythm, entire food webs would collapse or evolve into something completely new. The nights would change too. Before electricity, the moon was the brightest object in the sky. It guided migrations. It influenced hunting patterns. It shaped ancient calendars. Without it, the nights would be darker than anything we experience now. Early humans might have evolved differently in such deep darkness. Predators might have hunted more easily. Our ancestors might have relied more on fire or developed sharper senses to survive. Even the development of culture could shift. So many early myths, stories, and timekeeping systems are based on the phases of the moon. A moonless Earth might have created different beliefs, different calendars, different structures for early societies. But the biggest change of all might be the evolution of complex life. Some scientists believe that Earth's stable seasons played a major role in allowing long-lived ecosystems to develop. Regular sunlight patterns and predictable climate cycles gave life a steady environment to adapt to. Without the moon, Earth's tilt could swing violently enough to wipe out life repeatedly. Complex organisms might never get the chance to thrive. Evolution might stall at simple forms. The moon also slowed Earth's rotation. Without it, our days might still be only 10 hours long. A faster spinning Earth would create stronger winds, harsher storms, and more extreme weather. Oceans would churn faster, and climate zones would shrink. Life would face even more pressure in a world already full of chaos. The planet without a moon is Earth on hard mode. Its tilt swings, its tides shrink. Its climate buckles and twists. Its nights fade into endless darkness, and the path of life itself bends into something far less certain. The moon did more than light up the sky. It gave Earth stability and rhythm. Without it, the world might still be alive, but it would be a stranger, harsher, and far lonelier place than the one we call home. In the modern era, it seemed like the Earth-Moon system was one of the most stable things in the universe. The moon moved in a slow, predictable orbit. Earth spun at a steady pace. Nothing looked dangerous or fragile about any of it. For a long time, scientists assumed it had always been this way. They imagined the moon drifting outward smoothly since its formation without ever facing real threats. But then new models, new data, and new ideas began to challenge that calm picture. The turning point came when dynamicists and planetary scientists started using high-powered computers to simulate the early Earth-Moon system with far more detail than ever before. They added the sun's pull, the influence of Jupiter, the shape of early oceans, the cooling of Earth's interior, and even the wobble in Earth's tilt. When the simulations ran, they showed something shocking. The Earth-Moon system had spent its early life brushing right up against multiple danger zones. The scientists expected gentle curves and smooth paths. Instead, they saw wild swings in the moon's orbit, sudden jumps in eccentricity, and moments where the moon almost escaped. The biggest surprise came when they discovered the evection resonance. When the moon's orbit lines up with Earth's movement around the sun can pump energy into the moon's path. This could stretch the orbit into a long oval. Before the simulations, no one imagined this resonance could be strong enough to nearly destabilize the moon. But when the models ran backward through billions of years, the resonance kept appearing. Sometimes it stretched the moon's orbit a little. Sometimes it stretched it dangerously. Sometimes it pushed the system right to the edge. Scientists stared at the results in disbelief. They realized the early moon had walked through these zones, like someone tiptoeing across thin ice. A slightly faster Earth, a slightly cooler mantle, or a slightly different tidal pattern could have made the ice crack. The moon might have been lost. Geophysicists studying ancient rock layers felt the same shock. When they measured tidal rhythmites, they found days that were much shorter and tides that were far stronger than expected. The numbers revealed that the moon used to be close enough to raise tides the size of mountains. Those massive tides meant huge exchanges of energy, and huge exchanges of energy meant the orbit could change rapidly. Again, the picture was not one of calm stability. It was a system constantly at risk of slipping into dangerous motions. Planetary scientists studying the moon's interior added more surprising pieces. The moon's crust carries signs of intense tidal heating early in its history. That heating fits perfectly with periods of high eccentricity. That means the moon did not always follow a neat circular orbit. It had been stretched before, maybe more than once. maybe dangerously. When all these discoveries came together, the scientific community had a moment of realization. The Earth-Moon system had not simply survived billions of years because it was naturally stable. It survived because it got lucky. The early system rested on a knife edge, where tiny differences determined the entire future of Earth. Many scientists described their surprise in simple terms. They had expected a sturdy system. They found a fragile one. They had expected calm evolution. They found chaotic beginnings. The modern Earth-Moon system looks peaceful, predictable, safe. But the people who study its past know the truth. It was almost none of those things. It was a near miss, a narrow escape, a partnership born not from certainty, but from the fragile balance of forces that could easily have broken apart. And now that we understand that fragility, the moon looks different. Not just a light in the sky, but a survivor of a cosmic struggle that almost ended before it began. When you zoom out far enough, the story of the Earth-Moon system stops looking like a rush toward disaster and starts looking like a slow-motion rescue. Not a rescue performed by a hero or a miracle, but by physics itself, stretching across 4 billion years. At the beginning, everything was chaotic. Earth spun so fast that a day lasted only a few hours. The moon hung low in the sky, glowing with leftover heat from the giant impact. The tides were enormous. The orbit was unstable. Resonances lurked everywhere, like hidden traps waiting for the slightest mistake. But the same forces that nearly tore the system apart also began to guide it toward safety. The first steps of that rescue came from the tides themselves. Every time Earth's molten surface bulged under the moon's pull, it drained a little energy from Earth's spin. That energy did not go into stretching the orbit forever. Much of it turned into heat inside Earth's early magma ocean. The rest pushed the moon outward at a slow, steady pace. As the moon moved outward, it left behind the most dangerous resonant zones. The farther it drifted, the weaker the sun's disruptive pull became compared to Earth's hold. The orbit began to smooth out. Then Earth cooled, the crust hardened, continents formed, oceans deepened. These new surfaces changed the way tides moved. They created friction that helped absorb even more energy. That friction acted like a safety brake. It prevented the orbit from stretching too far during moments when the sun tugged in rhythm with the moon. The tides became more complicated but less dangerous. The rescue continued through the slow change in Earth's tilt. The moon steadied that tilt, preventing wild swings that could have triggered climate chaos. Stable climate meant stable ice growth and melt. Stable ice meant calmer tides. Calmer tides meant a gentler transfer of energy into the moon's orbit. Every part of the system fed back into the next. Each shift made the next step safer. Over millions of years, the moon reached distances where the worst resonances lost their strength. The evection resonance grew weaker as the moon climbed higher. The stretching forces faded. Instead of wobbling into eccentric orbits, the moon began to settle into a more circular path. A circular orbit is harder to break, harder to destabilize, harder to escape from. It was a sign that the system had survived its most dangerous era. Even as continents drifted and oceans changed shape, the orbit stayed on the safe side of stability. By the time life appeared, the Earth-Moon system had crossed nearly all the dangerous thresholds. The moon was far enough away that the sun's pull could not easily stretch its path. Earth had slowed enough that the tides no longer pumped extreme amounts of energy into the orbit. The partnership that had been fragile for hundreds of millions of years had finally settled into long-term balance. What looks peaceful today is the result of billions of years of tiny adjustments. Each tide, each wobble, each shift in ocean depth, each change in Earth's spin, all of them nudged the system away from danger. The story of the moon is not just a story of a near escape. It is the story of a long rescue, a rescue carried out by gravity and friction and time, a rescue that turned a chaotic newborn world into a stable home. And every night when the moon rises, we see the survivor of that rescue, still drifting slowly outward, still following the path that saved it. The moon is still drifting away. Right now it moves outward by a few centimeters each year, so slowly that no one alive will ever notice the change. But over millions and billions of years, those centimeters add up. If you follow the math far into the future, the Earth-Moon system begins to look different from the calm partnership we see today. The slow rescue that stabilized the system is still happening, but now it is heading toward a new phase, one where gravity reshapes the balance again. The first big change will come from Earth's rotation. As tides continue to pull on the oceans and the continents, Earth keeps slowing down. One day, a full rotation will last more than 24 hours. Much farther in the future, it may last more than 100 hours. The slower Earth spins, the weaker the tidal push becomes. Eventually, Earth will rotate so slowly that the moon's orbital period will match Earth's day. When that happens, the moon will stop drifting outward. It will reach what scientists call tidal lock. Earth will always show the same side to the moon, and the moon will stay at a fixed distance. At that moment, the long outward journey that has lasted billions of years will end. But the story does not stop. As the sun ages, it will grow brighter. Its gravity will also play a larger role in shaping the Earth-Moon system. Over billions of years, solar tides could begin to dominate over lunar tides. When that happens, energy will start flowing differently. The balance that held the system steady will begin to shift again. In the far distant future, the sun's pull could even start dragging the moon slightly inward instead of letting it drift outward. But this will not cause the moon to crash. These changes will happen slowly, gently, almost softly compared to the violent early history of Earth. The bigger question is the one everyone wonders about. Could the moon ever actually escape? Could it drift so far that Earth can no longer hold on to it? The answer depends on how far into the future you look. Under normal physics, with no major outside events, the moon will not leave Earth. Once tidal lock is reached, the orbit becomes stable. The moon will not keep drifting outward forever. It will settle into a comfortable distance where Earth's rotation and orbital motion match perfectly. Escape becomes nearly impossible. For the moon to break free, it would need a huge amount of energy, far more than tides or normal orbital evolution could ever supply. Something dramatic would have to happen. A massive asteroid impact, a close encounter with another planet, a major shift in the sun's gravitational pull. None of these are expected. In the most distant future, billions of years from now, when the sun expands into a red giant and swallows the inner planets, the Earth-Moon system will be overwhelmed by the sun itself. Earth and the moon might be destroyed together, or the moon might become a wandering object as Earth evaporates. But that is a different kind of end, not escape, not a drifting farewell. Just the final stage of a star reaching old age. Until then, the moon is safe. It will keep drifting outward for a long time, then settle into a steady orbit. The Earth-Moon partnership that survived the chaos of the early solar system is not in danger of breaking apart. The moon will not slip away into the dark. The future changes will be slow, gentle shifts, not dramatic departures. The bond that almost failed in the beginning will hold until the sun ends the story for both worlds. When you trace the entire story of the moon, from its violent birth to its near escapes and its slow rescue, you eventually reach a moment that feels almost unbelievable. The moon did not just shape Earth, it shaped us. Without the moon's stabilizing pull, Earth would have lived through violent swings of climate and tilt. Seasons would have shifted unpredictably. Ice ages might have rolled in and out without pattern. Storms and winds would have grown stronger on a faster spinning world. Life might still have appeared, but it would have been forced to adapt to chaos instead of stability. Complex life needs time and predictability to evolve. The moon helped give Earth both. The tides shaped by the moon also played a crucial role. When Earth was young, the tides were enormous. They pushed water far inland and pulled it back again. Over millions of years, this constant motion created tidal flats and shallow coastal zones, places where life from the sea could slowly experiment with survival on land. These shifting shorelines created pools that dried and refilled, forcing early life to adapt to both water and air. Some scientists believe these tidal zones were the training ground for the first creatures to crawl onto land. Without strong tides, Earth might have remained a planet dominated by ocean life, without the steady march toward land-based ecosystems. As the moon drifted outward, the tides calmed, but they never disappeared. Even today, they shape the coastlines where countless species feed, breed, and migrate. Entire ecosystems depend on the rhythm created by the moon, and those ecosystems eventually supported early humans. The moon also lengthened Earth's day. Long ago, an Earth without a moon would have spun so fast that days lasted only a few hours. Rapid rotation would have created fierce winds and chaotic weather. But the tides acted as a brake, slowing the rotation little by little until the days stretched into the 24-hour cycle we live with now. Plants and animals evolved using that rhythm. Sleep cycles formed around light and dark. Migration patterns synced with seasons. Human beings learned to mark time by both the sun and the moon. Our entire sense of day and night is tied to the moon's influence. The moon even helped steady Earth's tilt, preventing wild shifts that could have destroyed early ecosystems. A tilt, swinging between extremes, would have created endless cycles of freezing and burning, stressing life to the edge of extinction again and again. Instead, Earth's tilt stayed within a safe range for billions of years, letting forests grow, oceans stabilize, and climates settle into patterns that life could build upon. When humans finally appeared, the moon guided them too. Its phases became the first calendar. Its brightness lit the night for millions of years before artificial lights existed. It shaped myths, stories, religions, and navigation. The moon was woven into human culture long before we understood gravity or orbital mechanics. And all of this happened because the moon did not break away. It survived the early resonances. It resisted becoming too eccentric. It avoided escape by the smallest margins. Its orbit stayed bound long enough for Earth to become a place where intelligent life could emerge. Now that same life looks at the moon and studies how close it came to being lost. One moon, one story, one species capable of understanding how fragile that story truly was. The moon is not just a companion in the sky. It is one of the reasons we exist to look up at all. When you step outside on a clear night and see the full moon hanging above you, it feels permanent. It feels timeless. It feels like something that has always been there and will always be there. But the true story of the moon is far more delicate. Every time it rises, it is a quiet reminder of how close we came to losing it before life even began. The moon did not have to stay. Physics could have let it go. In the early days of Earth, the moon was caught in a universe that did not care whether it remained or escaped. Gravity does not play favorites. It simply follows rules. And under those rules, the moon could have spiraled outward too fast, fallen into a stretched orbit, or slipped into resonances that pushed it beyond Earth's reach. Yet, somehow, through billions of years of tides and heat and shifting continents, the orbit settled. The chaos quieted. The danger passed. the bond held. When you look at the moon, you are seeing a survivor of a cosmic struggle that almost ended differently. Its presence is the result of tiny differences: the angle of an impact, the shape of early oceans, the thickness of a cooling mantle. Forces so small in the beginning that no one could have sensed them, yet powerful enough over time to shape the fate of an entire planet. That is the fragility hidden inside every moonlit night. If the moon had slipped away, Earth would be another world entirely. Seasons would tilt and twist, tides would weaken into almost nothing, nights would be darker and colder. Life might have stalled in the oceans, or evolved into something unrecognizable. We might never have existed at all, and yet here we are. A species able to stand on the surface of the world and look up at the very object that helped make our lives possible. A species that built stories around the phases of the moon long before it understood why those phases existed. A species that reached out and walked on its surface, holding pieces of ancient rock older than any living thing. There is something almost emotional in knowing how close the bond came to breaking. The moon's orbit is not just a path drawn by gravity. It is a long story written in Earth's tides and in the stone beneath our feet. It is a memory of oceans rising and falling, of continents drifting, of Earth cooling, of chaos turning slowly into stability. The moon stayed, not because it was meant to, not because the universe guaranteed it, but because the forces acting on it balanced just right, like a coin landing on its edge and staying there for 4 billion years. When you watch the moon climb the sky, remember that you are watching a fragile bond, a quiet success story of physics and chance. A bond that gave Earth its rhythm and its seasons. A bond that shaped the evolution of life. A bond that could have snapped but never did. The full moon is more than light. It is a reminder that even in a chaotic universe, some things hold on.